And we're ready to do problem number 9, which is actually a problem you've already done. One just like it on a test, actually. So here we go. Let's see what's going on. We're going to design boxes with a volume of at least 600. Squares are going to be cut from the corners. So it's the regular box that we make. We cut the corners out. And the paper was originally 25 by 20. We're going to fold up the flaps, make a box. But the volume has to be at least 600. So, who can remember what the volume equation will look like for a box like this?
25 minus 2x times 20 minus 2x times x.
Beautiful. That is the volume of the box. Length times width times height. And what we did normally when we did these was we said, okay, this is our volume. And we typed that into our calculator and we found the maximum. But that is not what's happening this time. This time we want the volume to be at least 600. So we have this equation right here to solve. Now we're going to do it graphically. And let's review a little bit about what do we know about our window if this is the piece of paper that we're working with. What are you going to do for your x's? Your x's are going to be between what? What's going to be your min and max?
0 and 10.
Yep. Perfect. Beautiful. 0 because x has to be positive, and 10 because that's half the smaller dimension. And then the y's, again, we don't want to go less than 0. Our volume has to be positive. And since I want to be bigger than 600, I think I might set it at 1,000 and just see what happens. Now you can graph this however you want. There are a couple different options. I think I'm going to go ahead and put this in as one equation and then put 600 in as the other equation. For me, that works best. It is not the only way to do it at all. But putting in the left side of the equation as one equation and 600 as the other equation, I ended up with the same kind of thing I always end up with. Something like this. Does anybody have a question about that? Are you getting something similar? If you did it the way I did it. Obviously, if you did the problem differently, you're not going to get that same picture. But is everybody okay here? Now, we know because we've done this before that these are the two places where the volume actually is 600. So I'm going to go ahead and find those 2 points where the volume actually is 600. How would I do that? If you set it up the way I have, what will I be looking for here? How am I going to find those points?
Intersect.
Yep. Second calc, intersect. Perfect. Now I'll go ahead and find those 2 points. I got 1.659 for one of them. And 6.159 for the other one. Can somebody give me a nod or a heads up or something? Thumbs up for that? Does that look okay? All right. Now, I want to make sure I answer the question, though. Squares are to be cut from the corners to make an open box with a volume of at least 600. So what size squares should be cut from here? Would you agree that all of this part of the graph is bigger than or equal to 600? So my x's have to be between 1.659 and 6.159. Would you agree that any x in that interval will give me a volume that's 600 or bigger? Be okay with that? All right, let's try the next one. Now, this one was a good warm-up for us because it was reviewed. The next one is the same kind of problem, but it's not a box. So read this next problem here, number 10, and tell me any thoughts you've got. Crying is not an option. We got to somehow figure this thing out. All right. So let's see. The cans have a surface area that is less than 1,000. So the surface area has to be less than 1,000. That's the key. So y'all know what a can looks like. It's a cylinder, right? So we are trying to figure out a formula for the surface area of a cylinder. Now, first of all, pretend you're going to make a can. Don't you need a piece for the top and a piece for the bottom? And those pieces are circles. And so the area of the top and the bottom will just be 2 pi r squared, because pi r squared is the area of the top, and pi r squared is the area of the bottom. So 2 pi r squareds would be your top and your bottom. Okay, so pretend you're making a can. Here's my can. I'm making a can. I've figured out how much I need for the top and the bottom. Right there it is. Now the rest of the can is this right here, right? Well, what makes that can? Isn't it just a rectangle that I have folded around like this? So the area of this piece of paper, here's my can, I've cut it and flattened it out. It's just a rectangle. So the area of this piece of paper is the length times the width. Now remember, when it was folded up, the bottom was the circumference of a circle. So the bottom of this piece of paper is 2 pi r. The height of the paper is h. Again, here's my can. Here is the bottom of the can. It is a circle. The distance around the bottom is 2 pi r, circumference. When I open up that paper, this is what was the circumference. So this is 2 pi r, and this is h. There is your formula for the surface area, And that's what has to be less than 1,000. Now, here's my dilemma, guys. Wouldn't I love to go to my calculator and put this in and this in and figure out where they intersect? That would be great. But what is the matter with that? Why will that not work? Sam, I love your little lagoon sign, but I need to see you. If you're taking a nap, I might come through the screen. Sam Tuttle. If anybody has Sam's number, feel free to text him or call him if you think that might wake him up. All right, back to my issue though. What's the problem? Why don't I just type this into my calculator like I want to?
You have 2 variables.
Exactly. Thank you so much for paying attention, Trey. This is problematic. Because when I put this into my calculator, I can put in 2 pi x squared plus 2 pi x, but I can't put that in. This happens to you all the time in calculus, you guys. This is a skill you're going to use over and over and over again, I promise. We got to get rid of that. So somewhere, oh, there's Sam. Somewhere in the problem, there is more information that I will be able to use to figure out what to do with this. Does anybody see kind of a critical piece of information that I haven't really talked about yet? The volume of the can has to be 2,000 cubic centimeters. How do we find the volume of a can? Volume of a cylinder? No one remembers? Figure it out. What's the area of the base? Pi r squared times the height. There is your formula for the volume of a cylinder, pi r squared h. Because I know that pi r squared h is 2,000, can I figure out an expression for h that I could then substitute in here? Yep. So here we go. I'm going to divide both sides by pi r squared. So 2,000 divided by pi r squared is the height. And then I can take this and plug it in here. So now my equation is 2 pi r squared plus 2 pi r times 2,000 over pi r squared. And that's what I need to be less than 1,000. All right, let's clean that up a little bit. We got 2 pi r squared. Okay, so the pi's are going to cancel. One of the r's will cancel. So 4,000 over r. 2 times 2,000, and r is left over. Now, can I put that in my calculator? Yeah, because now I only have one variable. So that's good. That's good. So now I'm going to go to my calculator, and setting up my window for these is not as straightforward as for the box problems. So you're just going to have to play with it for a little bit. Would you agree, though, that whatever x and y are, they have to be positive? X is the radius, y is the surface area. So I'm going to use 0 for both x and y. And then I'm just going to play around with it a little bit. Let's see. I know for y I'm going to need to be bigger than 1,000, so I'll go, 1,200. And then for x, I have no idea. I'm going to start with 20. Now, I may end up changing that. I'm not worried about it. I do it all the time. We'll put this equation in as one equation, 2 pi x squared plus 4,000 divided by x, and then 1,000 is my other equation. Now I'll try this window and see what happens. Oh, it's not bad. It's not bad at all. I got something that looks like this. All right, is everybody still with me? Everybody getting a picture that looks like that? Now your picture may look a little different if you have different dimensions here. These are the two places where the surface area is exactly 1,000. This was 1,000. I need it to be less than 1,000, so that actually would be in here. So let's find those points, just like we did before, second calc intersect. This one is 9.655. And the other one is 4.619. Now, what that means is, the question said, what's the radius of the can? It means the radius of the can has to be between 4.619 and 9.655 centimeters. Okay? But the question also asks about the height. It says find the radius and the height. So this would be my radius. These are my R values, because R was X. So these are my radius values. How will I find the corresponding heights? Don't we know what the height is? Didn't we say the height was 2,000 divided by pi r squared? So we'll just take 4.619 and figure out the h that goes with that. And then 9.655 and figure out the h that goes with that. Please do be careful when you type that into your calculator, because there are two things down here. You might want to put that in parentheses just to be safe. So 2,000 divided by pi times 4.619 squared. I got 29.839. I'm going to wait see if you got the same thing. There's a lot of room for my error here. And the other one I got is 6.829. So the radii range from about 4.5 to 9.5. And the heights range from about 7 to 30, roughly. Now, some of you are thinking, oh my gosh, why am I doing this? Kids, this is a really, really, really useful problem. Pretend you're the Coca-Cola company. You make a lot of cans, right? A lot. And so every bit of material that you can save would be a good thing. So minimizing the surface area would be great. But every can that you make has a given volume. So the volume for these cans was 2,000. That's non-negotiable. Your can has to have a volume of 12 ounces if you're Pepsi or Coke. So you want to make a can that has that volume, but consists of as little material as possible. This is a real life problem. I can tell you're excited by that. All right, let's switch gears a little bit. Actually, let's continue on with our word problems. You have a review packet that I gave you. It says review 2.6 to 2.8. If I didn't give it to you, or I know I gave it to you, if you don't have it, it's in Schoology. Just follow along right now. There are some word problems down at the bottom, and I want to make sure we take some time to go through them. So these are all review, or at least most of them, I think, are review. You've done them before. You're very, very good with them, I'm sure. But let's try number 7. So this is on the review sheet. 2.6 to 2.8 review. Problem number 7. Says with a calculator. All these are to be done with a calculator. Or can be done with a calculator. We're mixing up some candy. We're doing a mixture problem. Caroline Ward, do you remember kind of our general setup for mixture problems when we're mixing two things to get a final mixture?
It's like the amount plus the percent.
It's actually times, but yeah, you're right. It's amount times percent plus amount times percent equals amount times percent. Now, this problem is a bit of a variation because instead of percentages, we have prices, but it's done exactly the same way. That's what's nice about a general formula. It can be applied to all kinds of specific situations. So she wants to end up with 20 pounds of candy that costs $3.60. That's what she wants to end up with. To get that, she's going to mix a couple of other kinds together. So one type has $2.50 a pound, that's its price, and the other is $4 a pound, that's its price. How many pounds of each kind of candy does she need? Now, a mistake that is very frequently made is kids will put an X in both spots. What's wrong with that? What does that imply if I put an X in both spots?
That both the amounts are the same.
Exactly. And do we have any idea if both the amounts are the same? No. So I can call one of them X. There's no problem with that. I can call that one X. But I'm going to have to come up with a different expression for this one. And before you say why, I want you to think about what we just talked about. Too many variables. So I'm not going to put a y there. What am I going to put there?
20 minus x.
Exactly. Thank you so much. Now, for those of you that are wondering about that, stop and think. These two added together have to be 20. So x plus something has to be 20. X plus something has to be 20. Doesn't the something have to be 20 minus x? All right, let's solve it and see what we come up with as an answer. Go ahead, you don't need me, you got this. I don't know if I did that all right or not. I got 5 1/3 pounds of the cheaper candy and then 14 2/3 pounds of the more expensive candy. Sam, blink for me. All right, anybody have a question about that one? All right, let's do the next one. This is one of our, we're doing a project together problems. Who remembers the general setup for a problem like number 8 on this review? Read the problem. Who remembers the setup for it? Mr. Broderick, do you remember it?
Is it 1 over how long it takes them?
It's 1 over the first person alone, yes, thank you. And 1 over the second person alone. And those added together give us 1 over their time together. So John can do it in 3 hours, so 1 over 3. John's time alone is 3. If Mary helps him, they do it together in 2 hours. So their together time is 2 hours. How long does it take Mary alone? So Mary's time alone is X, and that's what we want to know. How do we solve that?
On a common denominator.
Yep, and there are lots of common denominators. I like to use the smallest one, which would be 6x. But you can use whatever common denominator you want. The whole goal is get rid of these guys, cancel these out. So 3 will go into 6 and leave me with 2x here. The x's cancel and leave me with 6. And 2 goes into 6x and leaves me with 3x here. Oh, that's an easy one. How long does it take Mary alone? 6 hours. Anybody have a question about that? All right, we gotta get one more done before you get to go to lunch. So next problem gives us an equation and asks us to find the amount of sales in 2011. So here's the equation. It's given to us. We don't need to figure it out. Tell me what you think we should do to answer this question. Do not make it hard. This is a very easy question.
Does X represent the years that passed?
It does. It tells us that in the problem. It says X equals 0 represents 1990. X equals 1 represents 1991, and so on. So yes, X has to do with the time.
Do we plug in 20 for X?
Do we plug in 20 for X? Let's talk about that. What do the rest of you think? We're plugging in something like 20 for X. I'm just not sure it's 20. Is that the right number? Maybe it is. What does everybody think 20 is the way we should go?
Is it 21?
I think it's 21. Does that make sense to you? Think about that for a second. Does 21 make sense to you if we're doing 2011? Is there some kind of agreement about that? Monica's yawning. Kunkel, I don't know what he's doing. Is anyone in agreement that maybe 21 is the right number? Thank you. So I'm just going to put a 21 right here in for the X. And I'm going to get my answer. 120 minus 500 divided by 29. I got 102.76. I'm not sure.
That's what I got.
All right, so if that's money, I don't know if that's sandwiches or dollars. It's kind of hard to tell. So I'm going to say $102.76. Okay? All right, our homework 2.8 is due Friday. And I guess I'll see you tomorrow or the next day. Come back at 2 o'clock if you want to do more math.
Thank you.
Bye.